In this video, we discuss our third learning outcome for lesson 6.2, which is all about finding a range of x values given areas or probabilities, given that our variable x is a continuous random variable and it's normally distributed. So here are some helpful tips and reminders for finding these values from known areas. First, I want to suggest that you draw a picture. These graphs are extremely helpful in visualizing, understanding, and successfully working with normal probability distributions. So whenever I start any of these problems, any problem in lesson 6.1 or 6.2, the first thing I want to do is graph that normal distribution and then label anything that they gave me. So if they told me a certain probability or a percentage or an area, if they give me an x value that was interesting, they said, all the x's greater than this value or all the x's less than this value. That's what I'm going to graph. And then once I know that I'm looking at something less than or greater than, then I'm shading areas to the left or to the right. So whether you're in 6.1 or 6.2, we always want to start by graphing. Another thing to watch out for is confusing z-scores with areas. That's probably the issue that most students have when they're solving problems in 6.1 and 6.2. Remember, z-scores are distances along that horizontal scale. They're also numbers of standard deviations above or below the mean. And areas are, well, true areas of regions under that probability density function. If we are given a z-score and we're using table A2 to find an area, remember that the z-scores are on the outside edge of table A2. So if I know a z-score and I want the area, I look at the outside edge and then I try to find the area in the body of the table. Now, areas are areas of regions under that normal curve, and these are found in the body of the table. So if someone gives me an area, I need to go to the body of the table first. If I have the area and I'm trying to find the z-score, I go to the body of the table and then I find the z-score on the outside edge. Students get confused with these two pieces of information when they start interpreting areas as z-scores or z-scores as areas. If someone gives you a z-score, you're looking at the outside edge and then you're finding an area in the table. If someone gives you an area, you're looking in the body of the table and then you're looking for the z-score on the outside edge afterwards. So just make sure you know what those numbers represent and you're looking in the right part of the table to find what you need. And the next tip is to make sure you choose the correct side of the graph, like the right side or the left side of the graph. Here you're just looking for keywords in the problem statement. So if a problem statement says that you're looking for a value separating the top 10% from other values, that top 10% represents the 10% of the area on the right, and then you want 90% of the area on the left. But a value separating the bottom 10% from the rest of the area would be on the left of the graph. You'd have that 10% on the far left and then the top 90% on the right. So make sure that you know what that top 10% indicates. Top 10% is on the right. Bottom 10% is on the left. That will help keep you on track when you're finding the right z-scores. Consistent with that is that a z-score must be negative whenever it's located on the left half of the normal distribution. So if you know you're talking about something like the bottom 10%, well, since it's less than 50%, any z-score over there will have to be a negative z-score, because any z-score to the left of the middle, the left of that mean of 0 must be negative, and any z-score to the right of that mean of 0 has to be positive. So remember, z-scores are numbers of standard deviations above or below the mean. So if a z-score is negative, what that tells you is that the corresponding x value is below the mean. So if I were to graph the x value and the corresponding z-score, both of those would be on the left of the graph, which is to the left of that mean. Now, if the z-score is positive, that means the corresponding x value is above the mean. Or alternatively, if you have an x value and you know it's above the mean, you should get a positive z-score. So the X value, that Z-score, it's all going to be on the right of the graph. It's when the X value is above the mean and the Z-score is a positive number. And remember, the Z-scores are numbers of deviations above or below the mean. So positive Z's are on the right and negative Z's are on the left. And lastly, probabilities and areas are always between 0 and 1, and they're never negative. So if you end up with a probability or area that happens to be negative or it happens to be greater than 1, that's questionable. Chances are you don't actually have a probability or area, or maybe you made a calculation error. If that happens, you might be looking at a Z-score. The most common mistake in section 6.1 and 6.2 is that students confuse Z-scores with areas. You might be looking at the wrong part of the table when you're looking something up, just for example. So one way that you can check your work is to check and make sure that all of your areas are numbers between 0 and 1 and they're never negative. Make sure that if your Z-score corresponds to an X value that's below the mean, it's negative. And if your Z-score corresponds to an X value that's above the mean, that it's positive. And then make sure you're following those keywords in the problem statement to draw your graph correctly. Okay. So now let me tell you the procedure for finding values from non-standard normal distributions. It's actually very similar to finding values from standard normal distributions. You just have an extra step. So the first thing I do in 6.1 or 6.2 is always sketch that normal curve and then label anything that's given to me. So if they give me some probabilities or percentages, I'm going to label those as areas under my curve, and then I'm going to shade the appropriate region. And then once I do that, I want to find the corresponding Z-score at that boundary of the shaded region, either using technology or table A2. I'm going to show you how to use Excel to find the corresponding Z-score. I'll also show you how to use table A2. Just remember, when you're looking up Z-scores using Excel or table A2, the areas in the table and the area given by Excel give you area to the left. So if we know an area to the right or a probability that's indicated to the right, we have to find the corresponding probability or area to the left in order to use that technology or to use table A2. Remember, when you're using table A2, areas are in the body of the table and Z-scores are on the outside edge. Then after you find that Z-score that corresponds to that area, you want to convert that Z-score back to an X value. And we'll just do that using this formula. This is just a rearrangement of the formula that we had for Z. We had Z equals X minus the mean divided by the standard deviation. If we solve for X, we get this. And then lastly, you want to confirm that your answer makes sense in the context of the problem. So make sure your areas and probabilities are between 0 and 1. X values that are above the mean correspond to positive Z-scores. X values below the mean correspond to negative Z-scores. And everything makes sense in terms of what they told you in the problem statement. That's a really good opportunity to find your error and then go back and correct it before you submit an answer to a problem, for example. So let's look at an example. It says, when designing equipment, one common criterion is to use a design that accommodates 95% of the population. Assume that heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. The question says, what would be the maximum acceptable height of a woman if the requirements for the US Air Force pilots were changed to allow the shortest 95% of women to be pilots? In other words, find the 95th percentile, of the heights of women. In order to do this, I'll share my paper with you. So the first thing I want to do is sketch a normal distribution. I want a visual of what I've been told. I want the 95th percentile for women. So that means I want to take this area under the curve and I want to separate it into the 95% down here and the top 5% over here. And we want the women who are in that bottom 95%. So we're allowing the shortest 95% of women to be pilots. So we're actually interested in this area over here. That percentage in decimal form is 0.95. This percentage over here in decimal form is 0.05. And so what I'm looking for is this. The area to the left is 95%. And let's see, what else did they tell us? We were told that women have a mean height of 63.7 inches and a standard deviation of 2.9 inches. And the question says, what would the maximum acceptable height of a woman be if the US Air Force pilot requirements were changed to allow the shortest 95% of women to be pilots? Okay, so basically, we want this X value right here. So if we can find that X value, then we know that women that are that tall or shorter than that would be eligible to be pilots. So let's go back to our PowerPoint. Okay, so first we sketch and shade the normal distribution with the height X that we want to identify. And that's what I just did. We're trying to find that X value. And I didn't label this on my picture. I probably should have. That mean is 63.7 inches. So if I'm looking for that 95th percentile, or that height of a woman that separates the 95% of women that are the shortest from the 5% of women that are the tallest, it better be larger. It better be more than 63.7 inches, because 63.7 inches separates the bottom 50% from the top 50%. So I know that I've done something wrong if I get an X value for the 95th percentile that's less than the 63.7 inches. So that's helpful. Putting that on the graph, the mean on the graph, is helpful for sense making at the end. Okay, so I know that the area to the left is 0.95, and I want the X value that goes with it. One way that I can find that is using Excel. So first I'm going to show you how to use Excel. There is a function that will allow you to find that X value called norm.inv. It's basically the inverse of that normal distribution function. Now it asks you for 3 inputs. Actually, I think it asks for 4 inputs. No, maybe 3. We'll see in just a second. It wants the probability or area to the left. And in our case, that's 0.95. And then you have to enter the mean of the normal distribution that you're talking about and the standard deviation of that normal distribution. So this is what I would do. I would go to Excel. Whoops. Sorry, I'm deleting all this stuff. There we go. I go to Excel and I'll type equals norm.inv. And when you select that function, it actually populates with what you're supposed to enter right here. So you enter the probability, the mean, and the standard deviation. So we have 0.95. The mean for our distribution is 63.7, and the standard deviation is 2.9. Close parentheses, and then you get that X value right there. So we get 68.4700755, and usually we want to round to 1 decimal place here. So we get 68.5 approximately. Okay, so that's one way of finding that X value. Notice that when we do that, we don't have to find the Z value at all. Now, if I wanted to, I could also use Excel to find the corresponding Z score. So I could say, well, let's use norms.inv So that's the standard normal inverse function. And then I just want the probability or the area to the left to be 95%. That gives me a z-score of 1.645 approximately, if I round to 3 decimal places. Oops. That's not what I wanted. That's what I wanted. There we go. So if I round to 3 decimal places, I get a z-score of 1.645, and this is my x value. Okay. But I don't have to find the z-score if I'm using Excel. I can skip right over that and find the x value. Now the second method is to use table A2. Now with table A2, you have to find the z-score first. So first we'll look for 0.9500. That's our area in the body of the table. Don't look for this on the outside edge because then you'd be looking in the wrong place. The area is 0.95, so we look in the body of the table. So go over here. If that area is more than 50% or more than 0.5, then I need to go to the positive z-scores, and I'm looking for 0.95 in the body of the table. Now, if you zoom in a little bit, you see we've got a couple of areas here, 0.9495 and 0.9505. So actually 0.9500 is exactly halfway in between this area and this area. And 95%, having an area of 95% to the left, is so common that there's an asterisk in the table. And then if you go down here to the footnote, and it says the area of 0.9500 corresponds to this z-score, of z equals 1.645. So that's good. That is exactly what we got when we looked at Excel and we rounded. Okay. So if you're using table A2, you look for that 0.9500 in the body of the table, and then normally you would go out to that left edge and that top row and find the z-score, but this time it was that area of 0.9500 was indicated by that asterisk. So we found the z-score by following the footnote there, following that arrow to the footnote. Now that's the z-score. That's telling us that the height we're looking for is 1.645 standard deviations above the mean. If I actually want to find that height, I have to use this formula. So I take the mean, 63.7. I add that z-score, which is the number of standard deviations above the mean, times a standard deviation above the mean. And then we get that. And again, if we round to 1 decimal place, we get 68.5 inches. Okay, so what this is saying, actually I want to share my paper with you now. Is that if the Air Force changed their height requirements to say that women that are 68.5 inches or shorter than that are eligible for admission to the Air Force to become Air Force pilots, then this would be the height requirement. You have to be 68.5 inches or less. That would allow the bottom 95% of women in terms of their heights to be eligible for being Air Force pilots. Now notice that that 68.5 inches is above the 63.7 inches. That's a very good thing. If it wasn't, then we would know that it didn't actually separate that top or that bottom 95% from that top 5%. So I think in the context of this problem, the 68.5 inches actually makes a lot of sense. So it's always a good idea to check that out. So here's our conclusion. If the height requirement were changed to allow women of 68.5 inches or less in height to serve in the Air Force or serve as Air Force pilots, then 95% of women would be eligible to serve. Okay, so that is how we convert from a known area to a known X value. And again, just a recap of that. First, we graph the region. So we're sketching it and shading it. And then once you sketch and shade, and you know that the area to the left is 0.95. And if they gave me the area to the right, I would label that, and then I would do 1 minus that area to get this area. But you should find the area to the left. And then you want to find the corresponding z-score. And you can use table A2 to do that. So you look for this in the body of the table. And then you go out to the outside edge to find z. Except for in this very special case where we had 95%, so the z-score was indicated by a footnote. And then once you have the z-score, you need to convert your z back to x. Z was equal to x minus the mean divided by the standard deviation. So if you solve this for x, you have x equals the mean plus z times the standard deviation. And then that gives you the x value. So we did this before in lesson 6.1. We're just adding this extra step at the end for lesson 6.2. Okay, so we can go from a non-standard normal distribution to a standard normal distribution using this formula, z equals x minus the mean divided by the standard deviation. Or we can take that and we can solve for x in terms of z to go from this standard normal distribution back to a non-standard normal distribution. The key concept here is that area in any normal distribution bounded by this by some score x is the same as the area bounded by the corresponding z-score in the standard normal distribution. So this corresponds to this, and this corresponds to this. We just have to use the appropriate formulas to get from the graph on the left to the graph on the right, or the graph on the right to the graph on the left. So that is it for lesson 6.2. I'll see you next time.